All right, so now let's discuss the vapor pressure of solutions. Um, there are two different cases, and in this lecture, I'm going to talk about the first case, the case when we have non-volatile solutes. These are solutes that are not apt to go into the gas phase. Okay, they are likely to stay dissolved in the solvent. Salts, for example, salts are not going to volatilize into the gas phase. So these would be classified as non-volatile solutes. So whenever you have something like a salt, a non-volatile solute, when you dissolve those kinds of solutes in a solvent, they lower the vapor pressure of the solvent compared with the vapor pressure of the pure solvent. So let's just think for a moment about why. Here I'm going to draw a little beaker, and let's imagine I have a sample of water in my beaker. Okay, so let's imagine I have a beaker with pure water, and then beside it, I'm going to draw a beaker with salt water, with sodium chloride dissolved in water. So we can think about what's going on when I have aqueous sodium chloride versus what is going on when I have pure water. And imagine that these are closed containers, and I'm thinking about the vapor pressure in the headspace above the liquid in each of these containers. So in the pure water beaker, every single molecule on the surface of the liquid is water. Okay, I'm drawing my little bent water molecules here. So in the pure solvent, in pure water, every molecule is volatile. Every molecule is subject to escape into the vapor phase. Whereas in my salt water, I have some water molecules on the surface, of course, quite a few, but I'm also going to have ions that are dissolved in that water, sodium and chloride ions. Now, what happens there on that surface is only the water molecules are volatile. The ions are not going to volatilize at all. So I have a smaller proportion of molecules on the surface that are subject to escape into the vapor phase. And what that means is that I'm going to have lower vapor pressure above the salt water than I have above the pure water. So this is just a way of showing why a non-volatile solute like sodium chloride lowers the vapor pressure of a solvent compared with the pure solvent. And we can actually calculate this mathematically using a relationship called Raoult's law. So Raoult's law tells us that the vapor pressure of a solution can be really easily calculated by taking the mole fraction of the solvent, okay, not the solutes, the mole fraction of the solvent, that's a little confusing, multiplied by the vapor pressure of the pure solvent, okay, and this is true at a given temperature because vapor pressure, of course, is going to be temperature dependent. So now I want to do an example where we put Raoult's law into action so you can see how it works quantitatively. A solution is prepared with 200 grams of glucose, C6H12O6, in 400 grams of water. So this is a concentrated sugar solution. What is the vapor pressure of this solution at 25 degrees Celsius? Now, to solve a problem like this, I need to know the vapor pressure of pure water. And that is a constant that you can look up, or you might be given it in a problem. The vapor pressure of pure water at 25 degrees Celsius is 23.8 torr. So now I want to solve this problem using Raoult's law. I want to figure out what the vapor pressure of the solution is by taking the mole fraction of the solvent. Now here, I have to be careful. The solvent is the water. So I want the mole fraction of the water multiplied by the vapor pressure of the pure water. All right, so I'm given the vapor pressure of the pure water. What I need to do now is figure out what the mole fraction of water is. So the mole fraction of any component is going to be the number of moles of that component over the total number of moles in the mixture. And I have water and glucose. So I'm going to be adding the number of moles of water plus the number of moles of glucose, which is C6H12O6. Now, I had 200 grams of glucose and 400 grams of water, so I need to do mole-gram conversions for each of those quantities. So I have 400 grams of water, and I'm going to multiply that by the reciprocal of the molecular weight of water, which is going to give me about 22.2 moles of H2O. I have 200 grams of glucose, which is C6H12O6, and I'm going to multiply that by the reciprocal of the molecular weight of glucose, which is about 180 grams per mole. That's going to give me 1.1 moles of glucose, C6H12O6. So now I can plug these values into the expression for mole fraction to figure out the mole fraction of water in this solution. The mole fraction of water is going to be equal to the number of moles of water over, so that's the number of moles of water, over the number of moles of water plus the number of moles of glucose. Okay, so this is the moles of water plus the moles of glucose. And that is going to give me a large mole fraction. Since I am talking about the mole fraction of the solvent, this number should be pretty close to 1. So now I can figure out the vapor pressure of my solution by multiplying that mole fraction. This is Raoult's law. I'm multiplying the mole fraction, again, that's unitless, times the vapor pressure of pure water, which is 23.8 torr at 25 degrees Celsius. And this gives me a vapor pressure of 22.6 torr for this sugar solution. So we can see how sugar, the non-volatile solute, glucose, lowers the vapor pressure of the solution compared with the vapor pressure of pure water. Okay, the vapor pressure of pure water is 23.8. When I add sugar to it, because that glucose is a non-volatile solute, it lowers the vapor pressure to 22.6 torr. As the mole fraction of water, as the mole fraction of the solvent decreases, you would get lower vapor pressure.